רשמו אותי פה שההרצאה צריכה להיות באנגלית, למרות שלא אמרתי שום דבר. ומה אתם מעדיפים? לי אין הדף ספרדית? זה יכול להיות נחמד. מישהו רוצה הרצאה באנגלית?
אתה צריך לשאול באנגלית, האם יש פה אנשים שלא דוברים עברית. בשביל זה.
Okay, so I will do this in English. And another question is that this presentation is mainly surrounding reverse engineering. So just to understand what do you guys do, does anyone deal with reverse engineering as part of his day job here? Did you ever play with disassemblers? Do you know what assembly is? Okay, I understand. Cool. So 0x3e9, which is 1001 next ways to die. So hey guys, my name is Yaniv Balmas, and I'm a security researcher. I lead the malware research team at Checkpoint, and I do some vulnerability research also. And that practically means I spend most of my days sitting and staring at binary code and assembly code. Although I've never been able to find any comments inside binary code, such as this screenshot here, but you know, there's something to maybe hope for. And now, since throughout the years I've been doing reverse engineering, there's one problem that seems to keep popping up again and again, a couple of times a day, and it's really irritating me. And not only me, it's, I think, irritating anyone who ever dealt with reverse engineering. And now, that problem is that, you know, when we do reverse engineering, we have two main methods that we use. Well, one of them is static analysis, and static analysis practically means that we open a disassembler, our favorite disassembler, in my case, IDA. I think also most of reverse engineers use it. And these tools have a lot of static information. I mean, they're really mature, they've been there for a lot of years, and they have tons and tons and tons of static information inside them. Really useful. And for me personally, if I could, I would start my reverse engineering and end it all within IDA. I would never leave it for a second. I just love it so much. And I know a lot of reverse engineers actually share this love of mine. However, this is rarely the case because in most cases we actually have to resort to the help of dynamic tools, and by that I usually mean debuggers. I mean, if you've ever done any type of reverse engineering before, you probably know this problem. You're going statically through the code, and then you get somewhere to a function call, and then you take a look at the function call and see the arguments being passed to this function, and you just love to know what would be the value of one of these arguments, right? It would just speed up your work a lot more than just reversing this value and seeing where the value, this argument is seeing where the value came from. And what you do in order to do that is you go to your debugger, you place a breakpoint, the program hits this breakpoint, you go there and you look at the value, and then all of a sudden you realize that you look at the struct, and then you have to go back to your IDA screen and define that struct, and then go back to the debugger and see the value at the specific offset inside the struct. And that is really very frustrating job. I mean, what it makes you do is just mentally pass information all the time from the static tools to the dynamic tools and back and forth and back and forth. And this is like, in my opinion at least, takes all the fun out of reverse engineering. That's really Sisyphic and really hard to do. I mean, it only sounds trivial to me that there should be some kind of solution that will know how to combine, how to bridge the gap between the static world and the dynamic world and bring all this information together in one single tool. Now, this problem is not new. I mean, it's been there since, you know, the early days of computing. When men invented reverse engineering, this problem was also invented. And there's been a couple of solutions along the years that try to actually approach this problem. And there's two types of solutions. And one type is just third-party tools that will do this. They will do static and dynamic analysis together inside this tool. And I'm not going to talk about this specific solutions, and that's because, you see, they are third-party solutions, and usually we need all the data being transferred again into IDA, because this is our main tool. And since we need to bring data back, so it's again mentally passing data back and forth, and that's not good enough. The solutions I'm talking about are going to be plugins, and more specifically, they're going to be IDA plugins that should theoretically combine this static and dynamic tools. So just quickly go over some solutions. One of the most famous ones is called IdExplode. It's again an IDA plugin. It uses Intel PIN framework. It's kind of a binary instrumentation framework for those of you who are not familiar with it. And this is used for bringing the dynamic data into IDA. And now it all looks something like this. If you look at IDA, this is here. Maybe if I can. Okay, so these here are the assembly calls, right? And this is all data that's being entered through this IdExplode thing. As you see, you have here a lot of data containing runtime values. I mean, if you see your var 8, then you will actually see the value of var 8 within runtime. And you see this inside your static analysis too, right? So some of the pros of this is that it's a very, very extensive framework. I mean, since it uses PIN, you can actually place callbacks on almost every place inside your execution flow. In memory access, in function calls, you really have a lot of flexibility in that, which is really cool. Another thing is that you have branch statistics, so whenever you get to some kind of jump instruction, you can see how many times was that branch actually taken, how many times it wasn't taken. That's really pretty useful when you're doing reverse engineering. Now, some of the cons of this is that all the data, as you've seen, is stored as comments. They're just placed there inside your IDB file. And that's, I mean, that's nice, but it's really hard to search through it. And if you're dealing with really large binary files, then it makes your life really, really difficult. Another thing is that Intel PIN frameworks actually works on only Intel architectures, naturally. Not only that, the plugin itself, IdExplode, was mainly designed for Windows. So if you're looking to reverse engineer any Linux application, then that might not be the solution for you. Second solution is called FunCap, developed by 2013 by a guy named Andrzew Doznovsky. I probably didn't get the name correct, but I'm sorry for that. Anyway, it actually uses the IDA debugging API in order to bring the dynamic data into IDA. Now that's really cool because you see that's how it looks like. Again, it's comments inside your IDB, and what it does is something really that I thought was really nice, and it doesn't bring you all the values. It brings you values only from function calls. So it actually places breakpoints on function calls, and then when this breakpoint is hit, it's going through the arguments and trying to pass the raw value and write it here in the comments, right? So again, it's a very intuitive solution, and since it uses the IDA debugging API, then actually every debugger that can plug into IDA, which is a lot of debuggers, you can work with it. So you can work with QEMU or the native x86, x64 debuggers. You can work with really a lot of stuff, and that's really cool. Now another very interesting thing it does is when you get an argument, it actually tries to see this argument, the raw value, is a pointer to a string. I mean, if it's a string. So if it's a string, instead of writing the raw value itself, it will just write a string, which is very useful, right? And I'm going to touch that a bit later. Excuse me? Totally free. Although you probably have to debug it a bit to make it work. Anyway, some of the bad things about it is that when you have any new threads being created during your runtime, it won't follow that. So that makes it pretty useless for any common application because there's a lot of threads being created all over the place. And another thing is that the argument offsets are actually calculated manually. So that means when it gets to a function call, it just goes to the stack, looks at the stack frame, and then divides that by 4-byte chunks, and then understands how many arguments are there. Now that might work for a lot of cases, but of course there are a lot of other cases where this will be just wrong. It will give you the wrong values. So that's it. Now, what's missing from these solutions? So there's a couple of things missing. First of all, the extracted data, as you've seen in both of these plugins, is actually written as comments in your IDB, and as I just explained, this is a problem because, again, dealing with big binary files, that's just not indexable, not searchable, right? Another thing is that if you want to enter or add your own functionality into these plugins, that will be, well, I actually tried it, and that's not really easy. because you need to understand the Intel pin framework and install everything, and for the FunCap thing you need to actually read through a lot of lines of code, and that's really not intuitive. It will take you a lot of time to enter your own functionality there. And now last but not least, both of these plugins, or all of the plugins that are available, they have no reference to any value types. I mean, other than FunCap that actually brings you strings, but that's it. I mean, what does a raw value of an argument give me? I mean, if it's a struct, then what do I see? I only see the first member of this struct. I don't need it. I need the struct itself. I need to know the types. This is the most interesting thing here, because if I only have raw values, it doesn't really help me. I just have again to go to my debugger and see that it's a struct. So what did I do? So that was the main thing here, and this made me develop my own IDA plugin, which is very conveniently named Die. And that will be the topic of my presentation. I'm going to show it to you and maybe try to convince you how useful can it be for reverse engineering. So Die is actually short for Dynamic IDA Enrichment, and what it does is same as FunCap, just collect context of function calls and function returns. That's it. If something is happening within the function, we don't know it, right? But we do know all the arguments that being passed for function. This is actually very useful because this tells us most of the information we need. I'll convince you of that just in a minute. Another thing is that what we do is when we bring the values, we don't just write the raw values, we try to bring them in a human-readable way so that the reverse engineer, or the guy working behind the computer, will actually understand what those values mean, right? And another thing is, yeah, obviously, there's been a lot of work being done in order to do this very smartly, the interaction between static and dynamic. Again, you'll see this in the demos just in a second. And again, the other thing is that I try to use as much IDA magic as possible. IDA holds a lot of information, and I wanted to try and extract all the information possible. I didn't want to do any calculation myself. Whatever information I need, I wanted to go to IDA and query that from there. Okay? And actually, just a couple of weeks ago, this plugin, there's an annual competition of X-rays, the guys who do IDA. And this plugin won the first place. That's a great honor for me. Wow. So let me just quickly go through some implementation challenges of making this plugin. First of all, how can we actually query IDA for function arguments? I mean, okay, we have them there, but how do we use the API to query them? That's not a trivial question at all. It might sound like that, but it's really not. And the other thing is, once we get those values, then how do we parse them? And what values should we parse? How do we deal with that? And another thing is, now that we have the values, how do we do it with complex types? I mean, if it's a string, that will be like trivial, because we can just look at it as a string. But if it's a struct, what do we do, right? So that's another question, and I'll try to address them one by one very quickly. First one is function arguments. I spent hours and hours and hours digging into the IDA API, and if anybody ever did it, then you probably know that this could be a nightmare. And I actually did it, and I found this object, this type called tinfo_t object, which holds a ridiculous amount of information about types, right? This wasn't, wow, look at how many texts. It actually tells you for each argument, for each type, it tells you which type it is. Is it an int? Is it a pointer? Is it a character? Is it whatever? You just have everything in here, right? If it's a struct, then it tells you the struct, and you can query the members of this struct. Absolutely, everything is in here if you just dig deep enough. Nothing is, of course, documented, but if you read deep enough inside the code, you'll find all this. And another thing is that I dug up a little more and found these types, which actually gives me all the arguments information. So for every function, I can use this in order to query the arguments. And not only I can query them, but I can query where are these arguments being passed? How are they being passed to the function? I mean, are they passed on the stack? Maybe they're passed on the register. Maybe they're passed through a couple of registers. I don't need to do anything on my own. Everything is here, right? The location and the stack offset and everything is in here. And that's really cool. I mean, that's the whole base of that. Now, about the values, now that we have the arguments, I mean, I tried thinking about what should we parse, and I came to the conclusion that it was kind of impossible to try and imagine which parsers will be useful to people. So it only made sense to make some kind of extensible like plugin framework where you can write your own plugin or your own parser and just plug it into the system, and then that will be parsed now. And that's what I did, and it all works something like this. So you have what I call a value parser plugin, right? It gets two inputs. One of them will be the argument type that we gathered from the T-info-T object before, and another will be the actual value, the raw value that we actually see in runtime. And now there's two outputs to it. One will be a human readable value, and the other will be a score, right? So let me just give you an example. If we, for example, detected the Boolean type being passed and the value is 1, right? So this parser can actually tell us that the human readable value is true, right? And the score is 10 because we're absolutely sure that that is the value, because it's a Boolean and the value is 1, right? Now the problem is, sometimes for functions we don't have symbols, so we don't know the argument type, right? Then what happens then? Then you can see this case when the argument type is unknown, right? But the raw value is 1, the parser can still guess. It would say that if this was a Boolean value, then the value will be true, and the score now will be lower, right? That's a very easy scenario, but think about it. I mean, I can do it for strings. For example, I can guess if it's a string and give the score based on the length of the string. And this is all configurable through the plugins that you write. I write. Now, about complex types. So what do we do when we encounter not a Boolean value, but a struct? Well, that's pretty simple. We just break them up until we get to the simple types, right? So if we got a struct, right, we just need to query its members, and then for each member, pass those members to the parsers, and then go on again and again and again until we get to the very basic types. Now this is all done. It's stuff like this. For struct use, that's what we do. For arrays, we can again use the T-info-T object in order to get the array value, the array members. And for references, we actually have functions that lets us dereference. So if it's a pointer, we can actually go to the place this pointer is pointing to, and then look at the value there, and again and again and again, until we get to the simple types. That's basically it. Now there's a very nice animation I prepared here to show you how that works. So this is IDA. Nice, right? Now IDA has two main parts. One is the disassembler, which is the most famous one, the best one, and the other will be the debugger, right? Now most people who deal with IDA hate the IDA debugger, and I think that rightfully so. But it does have a very extensive API that lets you plug into it, right? And this API lets you plug into the debugger and into the disassembler, right? Now DI sits above all this, and it actually uses the IDA API in order to interact with both of this. Now, DI itself is composed of several parts also. One would be DI core, which is the main functionality of DI. And now we have the value parsers. These parsers I talked about, you can plug into DI, right? And the other thing, which is very important, is the DI-DB, where we store all the human readable values and all the data that this parsers output, right? Now, take a look at this code here. Just for those of you who don't read assembly, I will go through it really quickly. So this is the main function here, right? And there's two calls to functions. Here's one and here's two. This function here, function 1, actually has two values being passed through it. One will be just the value 1, right? And the other will be a string passed through the EAX register, and the string is str1. Now for this function, IDA knows the symbols. It knows the value types, right? Now this function here is an unknown function, which IDA doesn't know the types, just sees them as it is. And this function is being passed just one argument, and the argument is the same as here, str1, right? So we're starting DI, and what happens is that the assembler starts working. It queries this function that we're at for all function calls and places breakpoints at them. Right, now the next thing is the debugger gets an instruction to start a program, execution starts, and the first breakpoint is hit. Right? Now again, the debugger is getting an instruction to step into this function, and we step into this function, and here we see it, function 1 gets, you see, two arguments, and we know them, so IDA just places car star here and int here. And now what we can do is query those arguments using this T-info-T object that I talked about before. So the first type will be a string type, and this will be passed now to the value parsers, and since we know it's a string type, then the string parser will be pulled out and try to parse this, and str1 will be parsed. And this is the actual thing that will go into the IDB. And for the other thing, the other argument, so it's an int b, it goes into value parsers. We don't have an int parser, so the raw value 1, which makes perfect sense, right, goes into the IDB. Now, what happens now is that we iteratively try to place breakpoints at call instructions inside this function now, right? And we place them, and we continue execution, and now the next breakpoint is hit. In this example, this breakpoint is actually a library function, string compare, right? And that's a really big question. I mean, do we want to keep digging into this function? Because it's a library function. It's not really interesting, I mean, in most cases. So I actually put it as an optional configuration. You can choose to dig into that, or you can choose to just bypass that. And in this case, we'll just bypass it because it's not important. And go on. So now the debugger is getting the command to continue execution, and we go back out into our main function. And there's just one more thing left to do now, which is to query the return value of this function, right? So the return value here is bool, and this bool is set to the value parsers. Again, we parse that, we see that it's true, and we pass it to the IDB. And now we continue execution and get to the unknown function. Now what happens in this unknown function? First we step into it, right? And this is the unknown function. Now when IDA doesn't know the value types, it just says it's an int. That's like a default thing. And what we do now is just take the value of this row argument, right? And we pass it to the value parsers. And since we don't know the actual type, what will happen is that all the available parsers will try to go through this value and say, hey, I think that this is a string and this is the value. So you see, the first thing is that I will say, I don't know what it is, so first of all, I'll put the raw value in there, okay? And I state that this is a guess type. And then the string parser will say, hey, I successfully managed to parse this as a string, and I give this a score of 6, okay? And we store this as str1 inside IDB. And that's practically it. I mean, that's the whole magic behind that.
Can I ask a question?
You can try, and if it's too long, I will answer it.
I just have a small question. Are you able to cover all code flows, or only something that you are going to execute?
First of all, since I use a debugger, so only what executed in runtime, that's the only thing I'll see. If there's any branch that's not being executed, I'm completely blind to it. You can maybe, make execution go there, and then I will use it, but that's the unfortunate limitation of that. So, value parsers, yeah, they are the real magic behind DI. They're the real thing that makes DI work. Without them, DI is just a simple script. Now, let me just go through. We actually wrote these plugins as we went along in order to assist us with some reverse engineering jobs that we had. And I'm just going to quickly go over some of the basic parsers that we have. One of them would be a string parser. I already talked about that. That's a pretty simple parser. And actually what it does is uses, again, IDC, which is the IDA API, in order to understand which string it is. So we can support ASCII strings, Unicode strings, Pascal strings, and a whole bunch of other strings that we never heard about, but we support them. Another thing is a Boolean parser. Again, very easy one. If it's 1, then we say it's true. If it's 0, we say it's false. And then we have function parsers. That's really pretty interesting. I mean, if a function is being passed an argument that is the address of another function, of the beginning of another function, then instead of writing this address, we just state the function name. I mean, you understand what's going on here? This is probably some kind of callback, being passed to the function. And instead of seeing the raw value, you actually see the function that is the callback. That's really, really useful. And the same thing goes for modules. I mean, if, let's say, for example, kernel 32 is being passed into the function, and instead of writing the address of the loaded kernel 32 module, then we just see the name, kernel 32. And again, that's very, very useful for us. Right. Now, we have some more advanced parsers, and I have here 2 examples to show you. One of them would be handle parser. Now, everyone who ever did reverse engineering knows that this is a really big problem, because handles only live actually when on runtime. When runtime is finished, then we don't know the handle value. So what we do with this parser is when we get raw value, when we know it's a handle, it also only works on Windows right now. We just use these 2 APIs, Windows APIs, which is duplicate handle and anti-query object, in order to get the handle name and its value. So if, let's say, a file handle has been passed to a function, we actually know that that's a file handle, and that's the file it's referencing. So That's really, really, really useful. All right. And now another parser that I actually used in one malware research that I did. So this malware actually used basic strings, which is STD type strings. Now I didn't know a lot about the implementation of them, and it turns out that it's something really strange that looks like this. This string is really a complex type, and in offset 4 of this class, right, there's a union. And this union has 3 elements in it. So it's a buffer, a pointer, or an alias. So that means that this string can either be in offset 4, can either be a string or a pointer to a string. Either a string or a pointer to a string. So when you try to reverse engineer it, you have to go to offset 4 and then check, is it a string? No, well, maybe it's a pointer to a string. Well, it doesn't really make sense, but you know, somehow this thing works. I don't know why, but that's how it works. And that's actually a very, very good example of kind of an ad hoc parser, because we don't really need to understand the implementation of this. All we need to do, what the parser needs to do, is just to go to offset 4 and then check. Is this a pointer to a string? Great. If it is, then it's an STD string. Or it's like, yes, it's an STD string. And if not, is the string? Okay, great. So if it's a string, again, it's an STD string. And just one point is that if we go to offset 4, we better also check that offset 0 is not a string. Otherwise, we'd just be looking at some kind of substring. But just a minor point here. That's basically it. That's the basic strings. And that's how we deal with them. And that's pretty much it. And now I'm going to show you some demos, hopefully, praying to the demo gods, everything will work correctly, and you will see how effective that is. So, my first example is going to be this one. There's a certain firmware upgrade utility, and it actually has some kind of very, very easy but very simple password protection to it. And I actually tried to do this thing without die, and for me, and I consider myself a pretty experienced reverse engineer, it took me about 15 minutes to do this, right, to get to the password, or to be able to bypass it. And now I'm going to show you how easy it is using die, and along the way I'm going to show you die. So let me try and set this up here. Whoa, I can only see it over here, so you guys have to help me a bit.
That's it.
Yeah, did they go out already? So, this one is password protection, right? Good. So this is the utility here. See? Just simple password. We enter a password and it says incorrect and throws us out. So what we do now is just load this into IDA. I just drag this into IDA. And first thing you'll notice when you start up die, just a second. Okay. Finished? Yeah. Okay, first thing you notice when you load up die is this nice ASCII art here. Yeah, which is one of the best features that I actually have. Cool. So, okay, this is our application, and this is die. You see you have a new menu in IDA named die. And can you see this well in the last few lines? I have this zooming thing, right? So what do we have here? We have a load IDP, we have some configuration settings, we have a couple of views that I'm going to show you in a second, and then we have here 3 very nice options in order to start die. One of them will be to debug entire code, and when you choose to debug entire code, what it does is just goes through the entire code and places breakpoints at call instructions, and only then starts the execution. Right? And the other thing, go from current location, does exactly what I described a minute ago. It just places breakpoint on the function you're currently in, and then iteratively keeps placing breakpoints within each function it goes into. Right? And another thing is you can also do custom scope, which lets you choose like from this function and to this function if you have a really large binary and you want to just debug a small part of it, or just a specific function or something like that. Right? So I won't take you a lot through this, and let's just start die using what I told you, go from current location. So I'm actually placing myself inside with main, right? And go from current location, and how that works. So execution is of course a bit slower than it usually is because all of this parsing is being done in the background, but still it's pretty responsive. In just a few seconds we're going to see the message box popping up. Yep. Does anyone have any jokes, maybe? Anyone? I don't. Alright, here it is. So this is our upgrade utility, and we're gonna write here something like, I don't know, OWASP 2015. It's a bit slow. Okay, that's it. Let's hit OK. And I expect it will throw me out because it's not the right password. Right, and that's it. Execution is finished. Just a second. Boom, that's it. I'm out. Okay, so now let's go through the main views. There are actually two main views for that. One is called a parser view, and the other, value view, sorry, and the other is called function view. So let's start with function view. So this is what you see in function view. You actually have a list here of all runtime functions. All of these functions have been actually called during runtime, yeah? And the other thing is that you see how many times it has been called, and the other two things here are one, it checks it if it's an indirect call, right? So indirect call means it's a call to some kind of register that gets its value in runtime. So you don't know statically where it came from. This will be my next example. And the other thing is it tells you if this is a new function. I mean, if this function didn't exist in the original static analysis and it exists now in runtime, then I mark it, right? So I know that this is a new function, something that's being created right now. Now let's take a look at how it looks inside these functions. For every function, we have the exact spot where it was in the code where it was called. And for each position where it was called, I also have a couple of occurrences that it might have been called. So for example, if the call happened inside some kind of a loop, then we can have many occurrences for the same call in the same position, right? So in this position, for example, occurrence 0, you see, we have here all the function arguments and their values. So this here is a string, yeah, LPCSTR, and this is its name because we know the symbols, and this is the value being passed when the function call happens, right? And this is, for example, the return argument, so we only have value for return arguments on the values that we can see here, that are the values of these arguments when the function returned, right? So that's how it pretty much looks like. And now let me try and maybe see something a bit more useful. What do I have here? Okay, let's see. So, see any communication maybe function here? Just a second. I'm looking for a WSA startup something. Tell me if you see it. Where? Okay, so I'll try to speed it up. So, where? Yeah. What level? Okay. So this is really nice, right? Look at this. What we have here is two arguments. One of them is an LP WS data, okay? So an LP means it's a pointer, right? So instead of just bringing you the pointer value, we just dereference it, and it actually dereferences a struct value, right? And we also know this struct and we know its type, so we can enumerate all its members, and again, get all the members values on function call and on function return. I mean, that's really nice. That's a really nice thing to have. Now, okay, so I'll try to do it quickly, and probably won't get to my next examples. So the other view we have here is a parser view. value view, I mean. And value view actually gives you quite a different view. It actually shows you all the values that we've been able to detect during runtime, right? So we have here a lot of types. We have here threads. Where they go? Value view here. So you can see these here are all the values that we have. Modules, functions, each of them corresponds to a parser, right? So if we look at functions, then we can see all the functions that we've seen during runtime, and for modules it's the same. And now let's take a look at strings. So we've actually entered in the password the string OWASP 2015, right? So we expect to see this string somewhere in runtime, right? Now, tell me if you see this, because I really don't see anything in here. So we're going to look for that in the strings. And tell me if you see OWASP 2015 in here somewhere. Where? OWASP 2015, right. So that's really interesting because we see it, but where was this value actually used? So we just double click this, and boom, we got to the function where it was used. And what do you know? This function is being passed through arguments. One is OWASP 2015, and the other is, read it with me, A10 2015 1013. Somebody please remember this because I keep forgetting it. And we expect this to be the actual password, right? And what is this function? What do you know? It's a string compare function, huh? Okay? And if we double click this, and we see where it's used, yeah, it's used here. And now let me just show you that I'm not just bullshitting you. Let me open here the password protection thing and go there. And please tell me the string because I forgot it already. It's A10 2015 1013, which is the date, right? And boom, we made it, right? So, thank you. So how long did this take? Without the explanations I gave you, it only took me like 2 minutes to do this, right? So instead of 15 minutes, 2 minutes. I mean, think about how much time can this save you in your reverse engineering session? Because reverse engineering usually takes a lot of time, and if this saves you like 90% of the time, then it's crazy, right? So. Just quickly go back to my presentation, and I'm not going to show you the other examples, although they are really cool, but you can also see the videos of them inside the GitHub page, so please, if you're interested, please go in and look at them. Really, really interesting ones. Let me just quickly go over the rest of my presentation. So first of all, there's some stuff to do. One of them is to handle tank functions. I'm not going to go into that, but it's kind of a problem because it's something the reps function calls, and then it breaks all the logic. It doesn't happen a lot, but it does happen, and we have to deal with it. Another thing is that complex function parsers. Again, I'm not going to go into that, but there's some another enhancement we can do on function parsers, and we do plan to. When I say we, I mean me. Unless somebody wants to help me with that. Another thing is better GUI and a much better database that we need. And I'm going to finish soon. And solve some very dramatic crashes which surprisingly doesn't have anything to do with me. Rather they have something to do with IDA, and we actually have a case open with X-Rays, and they're working on that. We're actually helping them improve this product. Now, it looks cool. Can I have it? Well, yes, you can. That is totally open source tool, and you can go to my GitHub page and just download it and see all the videos and everything. You can take pictures. I'm going to switch this soon. That's it. The most important thing is that if you like it, please contribute. Write your own plugins. Help DAI get better, help us change the reverse engineering world, right? Now I can't finish this presentation without giving some words to Tamir Bachal, which actually helped me a lot with this project, and he designed his own plugin for IDA on framework that's, I actually did a really heavy usage of it. It's called SARC, and that's the link. And please feel free to visit it and look at it. Really a very nice framework for IDA. And that's it, guys. This is the answer. Any questions? Yes.
You demoed it using the local debugger. Does it work with other backends like GDB and other architectures?
It will work. The question was, I use the local, the native IDA debugger, and the question is, will it work with other debuggers? And the answer is yes. Whatever debugger can IDA supports can work with this. This is why it's amazing, and it's also theoretically architecture independent, because you can use QEMU and do this on MIPS, for example, right? Any other questions? Wow. Okay, understood, I guess. Thank you.